Current mirror. A current mirror is an electronic circuit configuration that is commonly used in integrated circuits, ICs, and analog circuits to provide a stable and accurate replica of a current. It consists of a pair of transistors, MOSFETs, configured in a way that the output current is directly proportional to the input current. The basic principle of a current mirror is to use one transistor as a reference transistor, M1, that sets the desired current, and another transistor as a follower, or mirror, transistor, M2, that replicates the current flowing through the master transistor, M1. Here's a step-by-step explanation of how a current mirror works. A biasing voltage is applied to the gate of the M1 which determines the desired reference current on M1. B. The biasing gate voltage of M1 creates a transconductance which allows M1 to convert the input gate voltage into a corresponding output current. C. M2 gets the same biasing gate voltage, hence mirrors M1 current. Since M1 and M2 gates are physically connected, M2 tries to match its drain current to the drain current of M1. D. M2 attempts to maintain a similar current as M1 by adjusting its drain to source voltage. The goal is to match the drain currents in M1 and M2. In this configuration, R generates IR. By utilizing the transconductance properties of MOSFETs and maintaining the same gate biasing voltage, the current mirror creates a replica of the reference current in the follower transistor, M2. The issue with this kind of configuration is a VCC variation leads to a mismatch between reference current and output current. B. Resistance tolerance variation in system-on-chip could be as high as plus or minus 10%, which leads to a huge mismatch in reference and mirrored current. C. Threshold voltage variation due to temperature and process variation leads to a mismatch in reference and mirrored current. For this reason, this kind of current mirror configuration is not practical for integrated circuits. Moving the resistance to the source of M2 leads to a reference current completely independent of VCC variation. M2 is K times M1 in size. Add P-channel MOSFET Cascode to force identical current in both legs. Example of current biasing generation for P-channel devices for current steering, and current sourcing in analog circuits, and integrated circuits. It provides a stable and accurate replication of a reference current, allowing for consistent and precise operation of circuits. NMOS and PMOS bias circuit. The diff pair regulates the drain of M1 and M2. By keeping M1 and M2 drain at the same potential, it makes sure both legs have identical currents. Note, negative feedback is achieved by effectively increasing the output resistance at D of M2.